want to find L naught, again, the original length of that spring that goes from A to E. We want to exert 2 newtons of force in order to switch the light off. The spring that we've chosen for this application has a stiffness of 1.5 newtons per millimeter. What do we want to choose to be the object in our free body diagram if we're looking for what the original length of this spring should be? The purple switch in this picture, if we isolate that from everything it's attached to, that'll be good to use because it's attached to the spring, and since we're interested in things about the spring, that's going to be important to know. So if we isolate that purple switch, that's our object of interest for our free body diagram. When it's at rest, when it is in equilibrium here, it's 15 degrees off of the vertical, and there's an external force Q acting on it. Now we are doing the analysis such that it's just on the verge of flipping when Q is 2 newtons. And because I'm applying Q normal to the switch, I know that this 2 Newton force is going to be 15 degrees from the horizontal, if this is 15 degrees from the vertical. Okay, so that's the only applied force on it, or external applied force. What other forces are going to be acting on the switch? Forces or moments.
The spring.
Right, so the spring at point B there, it's going to be acting along its length. So if I put point A down here, the force in the spring will be directed from B to point A. Other forces that act on the switch. Right, it's pinned at C. So just like all the other pins we've seen in 2D, it doesn't allow the switch to translate left-right or up-down. So at C, I'll have some Cx value and some Cy value. And what other force or forces or moment acts on the switch, at least in our free body diagram step? There's a normal force at E where the bottom of that switch is resting against the wall. So there's this contact force. Now, like in the last one, we're looking at where it just breaks contact with the wall. But in the picture, we still will have EX, that normal force. The normal force is always normal to the surface. And since at that point it's a vertical surface, that means normal to that, we're going to have this horizontal force EX, which will go down, will drop to 0. At least we've accounted for all the forces acting on our object. There's no couples in this case, but we have all the forces that act on our object. And we do know, we can actually jump to that step here. Because we're analyzing this when it's just about to switch, I can right away say EX is equal to 0 and simplify some of the other things I'm going to do. In general, though, it doesn't have to be equal to 0. It's only because it's on the verge of switching where it's just losing contact that it drops down to 0. Our free body diagram is really not complete yet, but we're going to see that in a minute here when we start looking at our equations. So if we start summing forces in the x direction, I'll have Cx minus Ex, which is 0. I will have 2 newtons times the cosine of 15 degrees. And I'll have a component of Fk, but again, at the moment, I don't know what that component is going to be. So that would be a signal that I need another picture in order to solve this problem. So how can I find how much, or really what the orientation is of Fk? If I look at A, B, C, right, that is going to be, we can make a triangle out of it, and then like we did last time, I think, use law of sines or law of cosines in order to solve that triangle. And actually, we're going to need that information anyway, because ultimately we're looking for what the original length of the spring should be. We're probably going to need to know what its current length of the spring is also in order to find its original length. So we can make a separate diagram that just illustrates that triangle. So this just shows the geometry of this. I know that the distance from C to B is 15 millimeters. I know that that vertical distance, C to A, is 30 millimeters. This other leg is the current length of the spring. I can call that L prime. And the last piece of information I know is that this angle is 15 degrees, which by using alternate interior angles, I know that also this is 15 degrees. If I look at this just geometry picture, I have this leg, or this side of the triangle, this side of the triangle, and I know what the angle is between those two sides. So that's going to be enough information to be able to use law of cosines, and enough information then to use law of sines. Because really what I will need is this angle, so that I know how much of fk is in the x, how much of fk is going to be in the y. So if I write law of cosines, I guess I'll write these out of order here, but using law of cosines, L prime squared will be 30 squared plus 15 squared minus twice 30 times 15 times the cosine of 15 degrees. The only unknown I have here is L prime, so the equilibrium length of my spring is 16 millimeters. Here I can use law of sines because I know the same reasoning that I used last time. L prime is not the longest length I have, the 30 is. So if there's an angle that's obtuse, it's going to be this angle here. So law of sines is fine to use for this, I'll call it alpha, because I know it has to be acute. The sine of alpha over 15 is therefore equal to the sine of 15 degrees over its opposite length, which was L prime, which was 16 millimeters. That tells me that that angle alpha, right, so about 14 degrees. Yeah, it should be pretty close to the 15 since these are pretty close too. All right, so we'll call that a 14-degree angle, which means that this is 14 degrees here. That at least helps us with equation number 1, because now we can say how much of f sub k lies in the x direction. So again, breaking it down into its components, its x component points to the left, so it'll be minus fk. And from the 14 degrees, it's opposite the 14, so it's going to be fk sine 14 degrees. So from equation 1, cx we don't know, ex went to 0, and I have fk here as unknowns. In fy, I will have 2 times the sine of 15 from the applied force. I'll have cy minus fk cosine 14 from the spring. Equation 1, again, I have those 2 unknowns. I've just introduced a third unknown in equation 2. So between equation 1 and equation 2, I have 3 unknowns but only 2 equations. So again, it comes to the moment equation to be able to simplify this a little bit in how I can solve it. I have a pin at C, so that's likely going to be the best place to take the moment so that Cx and Cy are not going to appear in my equation. The moment equation, though, this is going to be a little bit tricky now to make sure that I get my moment correct, because I will still have a moment contribution due to the 2 Newton force and a moment contribution due to Fk. Ex goes to 0, so I don't need to worry about that. Cx and Cy will drop out to 0. What will the moment from the 2 Newton force be around C? This is a case, I'll say a relatively rare case, where we actually know what the perpendicular distance is of an oblique force. It's applied 15 degrees, but because I know it's normal to the bar, I actually know what that distance is the 25 millimeters. So in this case, I actually don't need to break it down into the horizontal and vertical. That would actually make it more difficult because the horizontal component, I don't know, well, I can find it fairly easily, but I would need to find that distance, which would be 25 times cosine 15. Then there would be the vertical component, so that would be 25 times sine of 15. This one actually turns out to be easier because I know the perpendicular distance is 25 millimeters to get to point C. So that's going to be 2 times 25 millimeters is the moment caused by that 2 Newton force. Around point C, that is going to be clockwise though, so this will be negative. The harder part though is the spring force at F, or applied at B, because this is not normal to the angle from DCE or DCB. So I can't just multiply it by 15 the way I was able to multiply the 2 newtons by the 25. This one I do need to break down, unfortunately, into its components. But again, I need to do it just carefully to make sure that I have the right sign on everything, the right trig sign on everything. So if I look at FK, this one I do want to break up into its horizontal and vertical components to do this. I'll start with the horizontal part. So the force that's horizontal is Fk, right, sine of 14. So I'm going to start by looking at the horizontal component of Fk. So here, that's just the force is Fk sine 14. I have to multiply it by its perpendicular distance to point C. So this is where now I have to, it's not going to be 15, it's going to be just the vertical part of that 15 millimeters, unfortunately. So the distance will be 15 times, again, I know the vertical, it's 15 degrees from the vertical. So this is going to be using cosine of 15 degrees. Horizontal component of the force times the vertical component of this distance will give me the moment caused by the horizontal piece of Fk as it goes around C. And this is going to cause a clockwise moment around point C, so this too is negative. Then I have to worry about the vertical component of Fk and its moment contribution around point C. So that's Fk cosine 14 degrees is the force and its distance. If I'm using the vertical piece of Fk, then I have to use this horizontal distance to get to point C. So in that case, I can use the 15 sine, since that's also 15 degrees here, 15 sine 15 degrees will give me the horizontal distance between that force and point C. So the distance here, 15 sine 15. And this too is going to cause a clockwise moment around point C, so this also is going to be negative. Looking at my equation 3 though, the good part here is I have only one unknown because I took the sum of moments around C. So the one unknown is Fk, which I can solve immediately using equation 3. So the force in the spring, when it's just on the verge of switching, I find that that force is 6.86 newtons. And it's negative, it's actually in compression. Going back to what I wanted to find originally, I want to find how long should this spring be originally such that this is the situation we get into that only takes 2 newtons of force. So what equations do I still need that I actually have not used yet in my equation step? So the force in the spring is its spring constant, which we were told, times its current length minus its original length. In my free body diagram, I assume tension. This equation also assumes tension, which is important because it turned out it was in compression. So I get 6.86, negative 6.86 newtons. My K value is 1.5 newtons per millimeter. I found my current length in millimeters also, so I can stay everything in millimeters. And again, newtons. This will be in newtons per millimeter. So as long as L prime minus L naught is also in millimeters, I'm okay. My equilibrium length was 16, and L naught is what I'm trying to find. If I solve my equation 7, this tells me, since my left-hand side is negative, that means that L naught should be greater than 16 because it's in compression, so it's shorter than it originally wants to be. So that means in my design, the original length of my spring should be 20.6 millimeters.